Coming up on Cracking Quantum.
I guess I started out by thinking about more broad physics and what is everything. Quantum physics is extremely niche and pretty obscure, but it is looking at some of the same fundamental questions that some art is also looking at. And superposition is another case where, again, it sounds ridiculous.
Yeah,
it just
absolutely.
sounds like crazy ravings of somebody who had a dream. But it exists and is used in technologies, but it just doesn't sound right, does it?
My name's Ash Lyons. Join me as I try and figure out what quantum science is really all about. Welcome to Cracking Quantum. So we were just talking about the fact that you live out on one of the islands around Scotland.
Yeah.
What is that like? Because, as we were just saying before we started recording, that to me seems like the dream. If you move to Scotland, that seems like where you want to be, just out there with nothing but the nature and the beautiful landscape around you.
Yeah, it's great. It's Cumbria, which is Scotland's most accessible island. So it's only 30 miles from Glasgow, and then it's an 8-minute ferry crossing. So it's really easy to get to. And my grandparents used to live there. So, so I've known it all my life. And it's, it's a huge contrast to being right in the middle of London for 20 years.
That's got to be the two ends of the extremes, right? Is small islands out off the coast of Scotland and middle of London.
Well, I always said to my friends I'd either live right in the middle of a city or out on a tiny little island. And I think they didn't believe me. But now I've done both. And they're really different. I think you get to a stage with a city where you just kind of, once you've done that, once you've been to all the restaurants and you've been to the shows, and then after that, it's just basically a traffic jam for no particular reason. So there's definitely not many traffic jams on the island.
Yep. Yeah, I can definitely see that. There's part of me that never has understood why people want to live in the middle of a city. I grew up the edge of a village in a relatively rural part of the country. To me, I'd much rather be out in the country. I don't get why people want to be around the traffic and too many people.
I loved it when I was there. It's where the power is. It's where things happen. And if you want to meet people, that's generally where it happens. If you want to work with the best people, that's where you generally work with the best people. But there does become a point where you're like, be nice not to have neighbours, wouldn't it?
Definitely. Or have neighbours that are only sheep or cows that stand in the middle of the road. Is there much sheep and livestock out in Cumbria? Yeah,
there's some cows and some sheep and lots of rabbits.
Because you mentioned traffic jams. That's where you get the traffic jams out in the highlands and islands, right? You've got a cow that just walks in front of the road and you have to wait for it to move.
There are no traffic jams. I've been teaching my daughter to drive there, which is good because the roads are quiet. But it means that she's never experienced a roundabout or a traffic light. So she may have to do some practicing on the mainland.
Yeah. Do you have to before you can take your test? I guess you must, right?
You used to be able to take your test on the island. You can't anymore. You have to go somewhere sensible. But I think my grandmother might have taken a test there, which is worrying.
A little bit, yeah. It makes sense that you'd have to go onto the mainland to at least experience some traffic.
Yeah.
So let's get on to the actual podcast.
Sure.
So I'm joined today by Gregor Harvie. Hi, Gregor.
Hello. Hi.
You are an artist who is interested in quantum.
Yeah.
So your background, you're telling me not too long ago that actually you've got a PhD in fluid dynamics or something along those lines. Correct?
Yeah.
So you've got quite a sciencey engineering background, and you are a qualified architect. Is that correct?
Yeah. So I painted all my life, but when I went to university, I studied to be an architect. And then after that, I did a PhD in fluid dynamics in relation to buildings. So how hot buildings get and airflow around them and things like that.
Yeah.
And I actually did it for lightweight buildings, so buildings that are with fabric roofs, for example, like sports stadiums, that sort of thing.
Yeah, okay.
And they get really, really hot and really cold very quickly.
Yeah.
So the temperature can change by 30 degrees in a minute, just when the sun comes out. So it creates this really odd thermal environment inside them.
Yeah.
So I spent a bit of time looking at how to simulate that, how to predict it. And then after my PhD, I was really lucky to get a job working on the Millennium Dome in Greenwich.
Oh, wow.
So on the design and construction of that, which was this huge fabric roofed structure.
Yeah.
And nobody quite knew how to create a controlled environment inside it. So I worked on that for 4 years, I think. And I was really lucky there that I got to work with some of the best architects and engineers in the world, but also some of the best artists. So it was really interesting to see how they approached being given a subject and quite a lot of money and having to create a thing that 10 million people were going to go around and interact with. So it was really that, seeing how they approached subjects and how they did things, that encouraged me to think, well, I could do that. So I went to art college and started painting.
So that was the point that you kind of went from the architecture and the science a bit more towards the art sides. Is that correct?
Yeah, I mean, I think in terms of architecture, the Millennium Dome, whatever people think of it, it wasn't received brilliantly by the press. But as a project, it was the best project that was ever going to happen in my lifetime. There will never be another one that is that creative and involves that many people right at the top of their game. So I didn't really want to do that and then go back to designing offices or, extensions for people's houses. I couldn't quite bring myself to do that. So I thought, make a change.
Yeah, that makes
Start with art.
sense. Yeah, that's fantastic. It's interesting to hear how you made that transition into art, especially given that, like you said, you've effectively been an artist your entire life anyway. But it is really interesting to see how people make those decisions to switch over into a completely different domain. So I guess, do you do anything related to architecture or fluid dynamics anymore, or is it 100% focused on the art?
I do a bit. So I set up a website 10 or so years ago, which is a knowledge sharing website for people in the construction industry. So that still runs, and that brings me in a little bit of income. So that's helpful. I think the transition to art, though, is one of those things where you just have to go for it. I mean, if you thought about it, you definitely wouldn't do it because it's so challenging to make money at.
Yeah.
You just got to go for it and hope for the best.
And this is obviously a world which is completely alien to me, but is it then about persevering and really trying to push, or is it about getting lucky? Is it a mixture of both?
I think to a certain extent, you've just got to do what you do, and it either works out or it doesn't. I mean, the purpose of doing it is not to make money, really. Yeah. So if you go into it with that, if you went into it with the attitude that how can I make money, that then isn't really pure art. That's architecture's like that. You can't design a building without a client because you need a lot of money to be able to build a building. Art, if you've got a piece of paper and a pencil, you can do it. So the thing is just to do it. And if somebody pays you some money at the end of the day, that's brilliant. But if you go into it thinking, how am I going to make money? It's probably the wrong thing to go into.
Yeah, that makes a lot of sense, definitely.
So the way that I've approached it on the whole is to pick a subject and then to explore that subject for a few years and develop some sort of exhibition that expresses that subject, and then often to move on and do something else. So I've done projects about sustainability, about population growth, about Alzheimer's disease, and then what's next has turned out to be quantum physics.
That leads us quite nicely into where you are now, which you are artist in residence for the quantum theory group at the University of Glasgow.
Yeah, I approached Stephen Barnett there, the professor, maybe a year and a half ago, just to ask if he would talk to me about it, because I'd been reading a bit and I'd been thinking about it a lot, but I thought I'd better go and talk to somebody that actually knew something about it. Because if you're tackling a subject like that, you've really got to get it right.
Yeah.
And it's such a challenging subject. I felt I had to go and talk to somebody that really knew something about it.
That makes a lot of sense. I mean, that's actually part of the motivation for me starting this podcast, is that the way that I learned to understand quantum was talking to people.
Yeah.
So that's kind of what I'm trying to imitate by running this podcast. Yeah, it absolutely makes sense. To really get to grips with things, there's only so much you can do by reading books or watching YouTube videos or trying to understand other ways. Like, really talking to people helps.
Yeah, being able to ask questions, I think, is really useful, because whatever book you read, whatever video you watch, there's always seems to be a crucial thing they don't cover, because they're not going to cover the whole subject, are they? I mean, obviously. So they just cover the little bit that they are trying to do, and it's always missing something vital. And of course, you can't ask a book or you can't ask YouTube. So to have somebody there where you can actually ask, and then Steve will get out a piece of chalk and start writing equations. So it's a good way of answering the particular questions that you have, rather than being given answers to the things that the person doing the thing thought you might need to know.
Yeah, that makes complete sense. Do you feel like you're in a much better place in terms of understanding than you were? You said it was a year and a half ago that you started talking to Steve.
I think I understand more about the culture of it, which is important. And I think I'm more confident in being comfortable about not knowing things.
Mm-hmm.
It's not really a subject that I think I or anybody else can fully understand completely. And you just have to be comfortable with that.
Yeah, that's 100% true. That there's always going to be concepts which are either ultimately unknowable or are open to interpretation within quantum mechanics. And you're right, there has to come with some kind of acceptance that I'm not really going to know everything that's going on, because it's not that it's too much. It's that sometimes there might not genuinely be an answer, and you have to kind of work around that.
Yeah, there's also the maths. I mean, my maths is pretty basic. I mean, I know what calculus is, but I'm lucky enough to sit in on the quantum theory groups. They have a meeting once a week where somebody will present their research, and invariably it will begin with somebody starting to write an equation, which for me is not that helpful, because I just don't know. Firstly, I don't know what the symbols represent, and the maths is way beyond me. I mean, it is like black belt maths, isn't it? It's just not for the faint-hearted.
Yeah, I'm 100% with you there. I'm 100% an experimentalist, so my math skills, I think, is probably going to be on par with what you're saying. If I was sat in those meetings, I wouldn't have any idea what they're drawing on the board either.
Yeah, and the problem with quantum physics, for me, is that a lot of the kind of the proof of these things which don't sound right, do they? I mean, they sound crazy. But the proof is mathematical.
Yeah.
So if you can't do the maths, you just have to accept what you're being told. And I really, really don't like that. I'm one of those people that I have to understand something from first principles, or I don't understand it at all. So here, when I can't do the maths, and I've tried, and I really, really can't, I've got no way of double checking anything that I'm told. I've just got to kind of accept it.
Yeah.
And the more I go on, the more I discover that's what part of quantum physics is the kind of accepting that there are things that you cannot know, there are things that you don't need to know. It still kind of works somehow.
Yeah, that's I guess the thing. Like, once let's say you've got some idea about how quantum mechanics should operate, regardless of whether or not you know how to do the maths, if the final result is also what you would expect, I mean, it's got to be true. That's kind of like the principles that we go by. I'm kind of with you along the lines of not being able to write down the maths. I think maybe a bit of a difference between the two of us is because I'm an experimentalist, I can at least try out some of the ideas I have, even if I don't necessarily know the right way to represent it in the language, which is maths.
Yeah.
So I think that lends itself quite well to getting more of an intuitive understanding and kind of like getting to grips with broad concepts that other people don't necessarily have the opportunity to do, just because I can play around with things in the lab and understand it that way. Yeah, I can try it.
Yeah. So I suppose one of the interesting questions for me is whether trying something and getting the result you expect, whether that constitutes proof or not.
Ooh, that's a very good question. At the end of the day, all that you're able to say is that I got the evidence, as in I have the data, and the data is the data, it's a reflection of reality.
Yeah.
But having the step between this is my question, this is my hypothesis, and this is what the data is telling me, everything between that is essentially interpretation, no matter what way you treat it, whether you use maths to explain it or whether you've got, let's say, some broad understanding that you can put in words to explain that. But how do you prove that bit in the middle is true? I think that's an open thing.
Yeah, so I mean, one of the things I've been struggling with at the moment is the Bell inequality, which is one of the things that we're trying to represent through the art installation I'm creating at the moment. So I'm no physicist, so bear with me, but I think the Bell inequality is taken as a proof of a lot of quantum physics and entanglement and non-locality and all that sort of stuff. But the thing that it's proving, so in the mechanism of entanglement, as far as I'm aware, isn't fully explained. So it's not properly understood how entanglement persists at very great distances, for example. So I struggle to know how you can think that you've proved something if it's not actually being explained. What you've done is you've got some results that seem to match with the prediction.
Yeah.
And that's great. But that, I don't know that constitutes as a proof. This
is actually the really tricky bit, specifically about Bell's inequality. So this is, for references, it's like you said, this is the way that you demonstrate that you have a system which is entangled.
Yeah.
Actually, what you are doing is you're putting some hypothesis forward that says, let's say I have two particles, and suppose that I can only believe classical mechanics. Even if there is some parameter that I don't know what it is, but it's classical in its nature, there's only so much correlation I will see between my measurement of particle 1 and particle 2. Like that, there is a bound that you can put on a classical measurement. And when we say that the phrase that we use is to violate Bell's inequality, that would show that you have a correlation which is stronger than the classical physics. So it's not so much proving that you have entanglement per se, it's more stating, I know that the connection between these two particles cannot be classical in its nature. It has to be something else. I have to use some other description. And then it's kind of by proxy that would say, oh, that description must be quantum. It must be entanglement.
Yeah. Yeah.
It's a tricky ground, definitely.
Yeah. I mean, that's one of the definitions of what quantum physics is that I was given, is that it's anything that can't be described by classical physics. So if you can describe something with classical physics, it isn't quantum physics.
Yeah.
Which I suppose is definition by negative, but...
yeah, but then also what do you define as classical physics? Do we count relativity as classical physics? It's definitely not the conventional physics that we would typically think of. As if we're thinking about the same kind of context, but conventional physics, we would have Newton's equations, and relativity takes that a step further and shows things that would violate those equations.
Yeah, and then if you have the challenge of trying to explain that to an audience who knows nothing about it through the medium of art, you've given yourself a bit of a problem.
Yeah, that sounds like an entirely different challenge. I was going to ask, what was it about quantum that really kind of attracted you? But I guess you've kind of answered this already in what we've been discussing so far.
I think it is currently this is the field that is doing the most interesting work. This is where the boundary is to our knowledge at the moment. And this is where people are discovering new, weird, truly extraordinary stuff. And if you want to understand a bit about what the things around us are and how they work right now, that's where you end up. Quantum physics is where it's at. So I guess I started out by thinking about more broad physics and what is everything. But you quickly find out that this is where the discussion is right now, or has been for the last 100 years. So yeah, this is where it took me.
Yeah, I think that's entirely true. I think I can definitely see the appeal if you're an artist of looking for something which is difficult to understand, or we know that there's questions that we're not answering right now, and that looking is something which is going to be really cool and interesting to explore. So I definitely see the appeal, although obviously I'm biased. I find quantum interesting, otherwise I wouldn't be here.
But it's also dealing with subjects that are quite familiar to art. So they're maybe less familiar in science, but things like uncertainty, randomness, consciousness, determinism and free will, duality. These are all things that art has been exploring for 100 years as well. And it's interesting that they're parallel channels of thought, really.
Yeah.
Handled in really, really different ways. But I think when we met before, I was talking about the fact that Einstein's relativity and Picasso's cubism emerged at almost exactly the same time in history. And it's not because Picasso was trying to paint physics. It's because that's what people were talking about at the time. People were talking about multiple dimensions and seeing things from different perspectives. And both Einstein and Picasso, they weren't aware of each other, but they were aware of the general conversation that was going on about those sort of subjects.
Yeah.
And they both tackled them in very, very different ways. And I see the same at the moment. Quantum physics is extremely niche and pretty obscure, but it is looking at some of the same fundamental questions that some art is also looking at.
Yeah.
So I think the challenge for me is not to try and be an illustrator of physics, but to bring something else to the subject, something of me, something creative to the subject, so that it's contributing something rather than just being a kind of another attempt to explain.
Yeah, that's perfectly clear, and for sure, for us to find the questions that we have within quantum science, we need some creative thinking, because if we follow the logical steps that we have from classical mechanics, it fundamentally doesn't make sense. It requires something else. It requires a new way to think about the same problems. So for sure, I definitely see the value of artists such as yourself getting involved and trying to find new ways of either expressing something or explore these fundamental ideas. Yeah,
and it's a subject where even the words that are used aren't very good, are they? I mean, it's
that's definitely true.
It's something I'm discovering. I was talking to somebody earlier about trying to explain this, or trying to explain what I'm doing to people that have no understanding of even physics, let alone quantum physics. That is really problematic. And I did a trial of a piece that I prepared, like a prototype, and showed it in a museum a few weeks ago. So I had these random members of the public coming through, and to see just the kind of the level that they're at and how challenging it is to even begin to talk about this subject at all.
Yeah.
Is difficult, but the words, I think, don't help. The words that are used don't help.
I think that's definitely true. I think we definitely have some language issues within, I guess within science in general, but specifically within quantum, that are not constructive for communicating with anybody outside that area. And it's because, I guess, something that happens quite naturally within any scientific discipline, you develop shorthand communication between each other. You express things in a certain way, using a certain word, with the understanding that you both know exactly what that means, or at least have some idea of what it means, even if the word isn't a perfect fit. The one that comes to mind to me is the word observer. We use this quite a lot within quantum. And that's kind of opened up a discussion of how quantum connects to consciousness potentially, but it doesn't even necessarily need to include that discussion. The word that we use, observer, paints the picture that it has to be a person looking at the quantum action that changes the situation. But is that true? We actually have no reason necessarily to believe that it is.
Yeah, but even words like particle and wave are probably not very helpful, because they conjure up things that people learned at school, which are not really, it's not really what is being described.
This concept of wave-particle duality is something which I think the way that we teach it, I see why we teach it this way, but I think you're right, it's not very constructive for understanding at the quantum level. We teach it this way because we can write down the approximations that we would need to say this thing is a particle. And we can write down the same thing to say this thing is a wave. But the reality is nothing is either particle or wave. It's always both, depending on the circumstances that you look at it in. In other words, wave-particle duality isn't a particle can sometimes act like a wave, or vice versa. It's everything. It's particle and wave at the same time. It all depends on the situation, the environment.
Yeah, and that sounds ridiculous, doesn't it?
It does, yeah.
I mean, it may be right. It may be verified by experimental results, and it's part of technologies that work. But it sounds ridiculous.
It does. I should probably add to that those circumstances it's not like they're super extreme circumstances. Most of the time, we would see something like an electron act as a particle. And it's only some very specific circumstances that we see the wave-like behavior. And vice versa if we're talking about something like a photon or electromagnetic radiation. And I think this is why it sounds ridiculous, is because most of the time, we actually see the circumstances that correspond to one of those extremes or the other, and it's very rarely we see the bit in between. But everything does still fit somehow in that bit in between.
Superposition is another case where, again, it sounds ridiculous.
Yeah,
it just sounds like the crazy ravings of somebody who had a dream. But it exists and is used in technologies, but it just doesn't sound right, does it? So and that's really, really difficult in trying to explain it to people, or trying to explain any of the basis of quantum physics to people, is that it just doesn't sound right. It sounds like people went off to a conference somewhere and drank too much.
Yeah, and for sure there's probably parts of quantum mechanics where that is true, where it's people taking an idea and running with it, and it is a little bit on the fringe and it's a little bit crazy. But these, let's say these common things that we talk about, so superposition, entanglement, wave-particle duality, these are very much tried and tested theories, as in we've done experiments that show that they pretty much have to be the case. I'm now thinking back to the discussion that we started with of how you measure if something is entangled. And okay, maybe there's debate as to whether or not you can actually say it's this thing that we call entanglement or whether it could be something else. But yeah, I think it, coming back around a little bit, I think it sounds so crazy because we're always just in one of those extremes where all this stuff is happening. It's just, you never see it. So you never take it into account. You never need to.
Yeah. So one of the analogies that we're using for the artwork is a spinning coin.
Mm.
So I'm creating these artworks that spin at about 400 RPM, and they have different image on the front and the back, and it combines at high speed to create this new sort of artistic superposition. And it's based on the idea of a spinning coin. And I guess one of the things that the spinning coin as a concept is interesting because we use it in daily life to introduce randomness. Mm-hmm. That's its point. You toss a coin and it removes your control from something. So it's an inherently random thing in our lives. But also, we all know the outcome. Mm-hmm. If tossing a coin, it's 50-50, heads or tails.
Yep.
And if you did 1 million experiments, you would get the right 50-50 percentage with extreme accuracy.
Yeah.
But you can do that without understanding anything whatsoever about the coin or the aerodynamics of its motion or anything, or how high it's gone or nothing. You don't need to know anything about it, but you know for a fact you're going to get 50-50.
There's a good discussion I had with Professor John Jeffers in a previous episode where we talk about this exact thing. Like if you've got a coin which is flipping, I mean, yes, if you modeled everything perfectly, you knew everything about the coin, you could predict which way it's going to fall, but you don't have access to that information.
Yeah.
So then it comes down to just this random 50-50 chance.
So this is one of the things about quantum physics being kind of probabilistic in its nature, is that makes it inherently accurate. Whether things are explained or not, it has an inherent accuracy just because of its nature.
This reminds me of another conversation I had with someone the other day where they were asking, if you've got, let's say, a single photon, how do you know it's a single photon? And the answer is, well, you kind of don't. What you do is you prepare the experiment over and over again. So you measure one photon, you test to see, is it a single photon or not? And you'll get an answer that, yes, it looks like it is, or no, it isn't. But if you repeated the experiment again, statistically, you might get a different answer because, like you say, it's probabilistic. So the only way you can show a single photon is a single photon is you measure loads of them and show statistically that they have to be single photons at a time. One photon doesn't tell you anything. Anything in quantum mechanics, and this is kind of like a general theme, is probabilistic, is statistical. So everything in quantum is tied very closely to everything that you're saying.
So have you got kind of when you meet somebody at a party, you've never met them before, have you got a go-to explanation that you reel out?
About how do I know a photon is a photon?
Well, no, either about what is it that you do, or what is quantum physics exactly?
If the question is what is it that I do, I tend to rely on the fact that people have at least a broad understanding of some of the words, even if they don't know exactly what they mean. So I might say something like, I build new ways of doing imaging microscopy that use quantum phenomena like entanglement and superposition to do something which is new and interesting.
Yeah.
But that's not really explaining anything about specifically what I do. The other thing that I might tend to do is talk about the applications, which could be really interesting. And that depends on how easy the applications are to understand, because sometimes it takes a few steps. Like you might need to explain that I try and build new types of microscopy, but that microscopy is used for this, which is then used for that, which is then used for something else, before you get to the final application, let's say. So it can be tricky when you've got these kind of complicated steps in between. I would say a shorter answer to your question is I don't tend to explain it all that much. I think this is true for a lot of people who work within quantum. You can use these terms that people have heard, but explaining what they mean, it does take a little while to explain them in a way that people can get a decent grip on what it is that you're talking about.
It was really interesting. So we trialed a prototype of this spinning image in a museum on the island. So it's bank holiday weekend, lots of people coming in. And the point of trying it was to see how much information can we get across to a member of the public, just how much. So there's quite a few layers of detail in the prototype about the things that it's capable of explaining. So how much can we get across to somebody who's just passing by? And the first hurdle was that to get it to work, there's a yellow button and they have to push the yellow button. And there's a big sign next to it saying, please push the yellow button. And people wouldn't push the yellow button. They'd come and look at it, read the sign, and then walk off. So you'd have to stop them and say, are you not pushing the yellow button? Oh, I didn't know if I was allowed. There's a sign there. So that was the first. But then, the amount of new information people are prepared to take on, when they're just out for a day out and they want an ice cream, is very, very little. So if you can get the idea across that this is a combined thing when it's in motion, and it's only when you do something and you stop it and you look at it, then it becomes a one thing or the other thing. And if you can get that across, you're doing really, really well. Beyond that, we didn't delve into the Bell inequality.
Yeah, I'm not surprised. It's all of these concepts are tricky because it takes the right kind of background to really appreciate what's being said. I think a lot like it requires the right information to already kind of be present. So even this notion of superposition, which arguably is maybe one of the simpler things within quantum to kind of understand, at least at its basic level. I would say to really understand what it means, you need some understanding of wave mechanics, because you need to be talking about concepts that where we use words like coherence to be able to actually get across what it means for not just a particle to be in two places at once, but to be doing that in a coherent way such that you get these specific states that we call superposition states. And obviously most people, as in general public, know nothing about wave mechanics, because why would they? It's something that's tends to be very specific to physicists, engineers, mathematicians, people who have some kind of STEM background.
But if you ask people about relativity, for example, they would probably be able to say something.
Yeah.
They'd have some vague idea about Einstein and something to do with space-time, and they'll have seen something on Star Trek, so they'll have a broad, you would be able to engage with them at least. Whereas quantum physics, I don't think you can. I don't think it's entered the popular consciousness in the same way, even though it's been 100 years. People don't have a way into it. It's not being popularized in the same way. And I think that in itself is interesting, because relativity is no simpler.
Yeah, and came from, like you said, around the same time. So I mean, Einstein was one of the big players in the development of both of these things in parallel. So they've got almost the same starting point.
But if you ask people, what did Einstein do? Almost none of them would say anything to do with quantum physics.
Before I move on from that, that's just reminded me, I was sat at home with my wife watching old episodes of Stargate SG-1, and there's a really actually pretty good episode where they are close to a black hole, and you see lots of these relativistic effects happen. And it's of course not perfect, it's science fiction, but there's a lot in there that lines up quite well, and there's no way a similar thing that uses quantum mechanics would have the same kind of quality of description as general relativity, because you're right, it's not something that exists in the public eye.
And there are no visuals, which is challenging for me.
Yeah, I can see the struggle there being an artist.
I mean, at least relativity's got a kind of a macro scale thing. It can relate to things that you could touch or feel or travel through or whatever. Whereas you just can't. There's nothing. It's a tiny little world that we have no experience of whatsoever.
And if you try and do something visual, you end up with complete nonsense. I mean, I like to joke that the Ant-Man films are the worst thing that's happened to people's understanding of quantum ever, because it's nothing there is remotely lining up to how things could possibly be. Like, even just going down to that scale is, in principle, nonsense. It's not something that could happen.
Well, it's interesting that because obviously when papers and articles are written about it, they have an image generally associated with it. And it will either be somebody in a lab doing something clever, or it'll be these kind of stock photo waveforms with some sort of light in the background. Those are so ubiquitous now that if you ask ChatGPT to create an image of quantum physics, it will source those. It thinks that's what it is. So it will produce images that are these kind of nonsense waveformy things with some sort of camera flare in them, because that's what everybody is telling that it is, but it just isn't.
That explains a lot. I've tried a few times getting ChatGPT to design logos or things for me that are in some way involved with quantum, and they're always terrible. And I guess this is the reason why. It's impossible to kind of present any visual which is representative.
Yeah.
Before we leave things, I wanted to ask you if you have a favorite random science fact that you'd be willing to share with us.
I do. I mean, this is something that probably everybody else knows, but I didn't know. But when I started looking at this, you become aware that there's less and less and less matter compared with what you thought there was.
Yeah.
So we live on a planet, so we're surrounded by matter, and we think there's lots of matter, and there's a solid desk in front of us and that sort of thing. But when you start to get down to it, it turns out that very little of anything is matter. So if you do a calculation, and I'm sure somebody will check this and find it's rubbish, but it's a very small number. If you do a calculation of how much matter there is as a proportion, a volumetric proportion of the universe, it comes out as 2.8 times 10 to the minus 44%. So that's 0.000, then about 40 noughts to 8%, which is nothing really. And if you were to look at the universe statistically, you wouldn't even notice matter at all. Yeah. Or you would write it off as an error.
That's a good point. Yeah.
Or you just think it was some sort of weird background noise.
Yeah.
But you certainly wouldn't focus your work on this stuff, which accounts for almost nothing. Yeah. So I think we're deluded because we live on a planet. If we were anywhere else, we wouldn't be looking at it at all.
But even like, let's take for granted we live on a planet, we're surrounded by matter all the time. Even the actual space that's there, as in the empty gap between the atoms and the molecules, between the subatomic particles, there's a lot of empty space.
Yeah. I mean, there's more of it here than there is anywhere else, but there's still not very much.
Exactly. Yeah, and going a bit further, when you get down to the really, really small scale, matter isn't necessarily what you think it is as well. We think of electrons as being these tiny little particles that whiz around an atom, whereas if you look at it from a quantum point of view, that's not really a good description. They're kind of like all around the atom, and sometimes we use the word cloud to kind of describe it, but it's not in a specific place. Yeah. And that just kind of adds to like more of the empty space.
Well, I think the more that people look at it, the less there is. And presumably there'll become a point where we do away with the concept altogether.
Just write off matter completely. We don't need it.
There's something, but we don't know what it is.
Excellent note to leave it on, I think. Thank you, Gregor, for your time. This has been really, really interesting. Thank you.
Thank you. Great to be here. You've reached the end of the podcast, which probably means that you enjoyed what you're listening to.
So please don't forget to like, follow, subscribe, and share this podcast series as much as you can. The more you do those things, the better this podcast is going to be. Don't forget, you can always contact me by email at ash@crackingquantum.co.uk. And please join me again for another episode of Cracking Quantum.